A faint silver blur above Earth can carry a harsher truth than any explosion in space. Andromeda is called our nearest major galactic neighbour, yet its light has been travelling for about 2.5 million years just to reach our eyes. If a message were sent there and answered, one simple exchange would outlast entire species. That is the strange scale behind this quiet object in the autumn sky, close enough to see, far enough to break the meaning of close. If this kind of calm cosmic journey helps you slow down and think more deeply, a like, a subscription, or sharing the video helps calm space science continue creating thoughtful science stories. Thank you for spending your time here. In the comments, share where you're watching or listening from, what time it is there, and whether this is part of your evening, study time, or quiet rest. Now the small cloud in the sky begins to reveal its true distance. Andromeda begins in the historical record as something modest, almost easy to overlook, long before it became a galaxy in the modern sense, before telescopes could separate its faint light into stars. It was only a soft patch in the northern sky, visible under dark conditions as a small blur near the constellation that carries its name. To the unaided eye, it does not show spiral arms, a bright central bulge, dust lanes, or the scale of a separate stellar system. It appears as a quiet unevenness in the darkness, a pale mark that could be mistaken for a thin cloud or a weakness in the eye. That first impression mattered, because for most of recorded history, astronomy had no reliable way to measure how far such an object truly was. Position could be recorded, brightness could be compared, motion across the sky could be watched over years. But distance, especially distance beyond the stars that seemed fixed, remained one of the hardest facts to reach. In the 10th century, the Persian astronomer Abd al-Rahman al-Sufi included this object in his book of fixed stars and described it as a small cloud. The description was careful for its time. It did not pretend to know more than observation allowed, seen without instruments. Andromeda really does look cloud-like, and nothing in the sky itself explains that the glow is made from the blended light of hundreds of billions of stars. Al-Sufi's record is important because it gives Andromeda a place in human memory. Yet it also shows the central limitation of early astronomy. The object was noticed and preserved in writing, but its nature remained sealed behind distance. The light had crossed intergalactic space before reaching Earth, but the observers who saw it had no reason to think in those terms. Their universe was organized around visible patterns, planetary motions, lunar cycles, and the fixed star field. A faint cloud among the stars did not yet demand a larger universe. It only demanded a label. That condition lasted for centuries. As telescopes improved, Andromeda became clearer, but not clear enough to solve the question. More detail did not immediately bring correct understanding. It often made the problem more complicated. Through early instruments, the object appeared extended rather than point-like, brighter in the middle and softer toward the edges. It belonged to a growing class of dim, misty objects that astronomers called nebulae, a word used broadly for cloudy celestial features whose true forms were not yet known. Some nebulae really were clouds of gas inside the Milky Way. Some were star clusters too dense or distant for small telescopes to resolve. Some were entirely different galaxies, though that category did not yet exist in a settled way. The same word covered several kinds of object because the observations had not yet separated them. Andromeda was therefore grouped with things that looked similar from Earth. Even when their physical nature was not similar at all, a category can be useful and misleading at the same time. It gathers observations into order, but it can also hide differences that only later instruments will reveal. By the late 18th century, Charles Messier gave Andromeda another identity. Messier was not trying to build a theory of galaxies, he was a comet hunter, and his catalogue was created in part to keep track of objects that could be confused with comets, but did not move like comets. These objects were fixed hazes, persistent lights, patches that might lure an observer into thinking a comet had been found, only to remain in the same place night after night. Andromeda entered this catalogue as Messier 31. The designation is still used because the catalogue became historically valuable, but its original purpose was practical and even negative. It marked objects to avoid mistaking for something else, in that sense. Andromeda was not placed at the centre of cosmic thought. It was filed away as a fixed blur that could interrupt the search for moving bodies in the solar system. The importance of that moment lies less in irony than in contrast. The object that would later prove the existence of other large galaxies was once treated as a background complication. It had not changed. The light was the same. What changed was the ability to ask the right question of it. For a long time, the dominant question was not whether Andromeda was a galaxy. The question was whether the Milky Way itself contained everything that could be called the universe. That assumption was not foolish. It followed from the evidence available at the time. The Milky Way stretches across the sky as a bright band of unresolved stars, and telescopes gradually showed that it contained enormous numbers of them. It was reasonable to think of it as the main structure of existence. If all visible stars belong to it, then perhaps all other hazy objects belong to it as well. Spiral nebulae, including Andromeda, were often interpreted as local features within this single system. They might be gas clouds, regions of star formation, or material arranged in rotating forms inside the Milky Way. The idea of island universes, separate stellar systems comparable to our own, existed as a possibility, but for generations it remained difficult to prove. The challenge was not imagination. It was measurement. Without a dependable distance, appearance could be interpreted in more than one way. A nearby cloud and a faraway galaxy can both look faint and extended when viewed from Earth. Brightness alone cannot settle the matter, because a small object nearby and a large object far away may appear similar. Shape cannot settle it either, because telescopes were limited by resolution, atmosphere, and exposure. The observer could see Andromeda, draw it, catalogue it, and compare it with other nebulae, yet still remain unsure whether the object belonged to the Milky Way or lay far beyond it. This is why the older descriptions deserve careful attention. They were not merely wrong in a simple way. They were responses to an object that concealed its scale almost perfectly. Andromeda is close enough, by galactic standards, to be visible without a telescope, but far enough that its stars blend into a single faint glow for human eyes. That combination is unusual. It makes the object appear accessible while hiding the fact that its light has travelled for a span of time longer than the existence of modern human civilization by a huge margin. The distance is present in every observation, but it is not visible as distance. It is translated into faintness, softness, and silence. For centuries, the evidence entered the eye without revealing the journey behind it. A person could stand under a dark sky, locate the pale haze, and feel that it belonged to the same celestial dome as the stars around it. The object seemed embedded in the familiar sky. There was no obvious sign that it stood beyond the Milky Way, separated from Earth by a gulf so large that even light needed millions of years to cross it. The historical misreading of Andromeda therefore begins with a simple human problem. The sky flattens depth. Everything appears projected onto the same dark surface, whether it is a planet a few light minutes away, a star a few light years away, or a galaxy millions of light years away. The eye receives direction, but not true distance. Astronomy had to invent methods for recovering the missing depth, and until those methods matured, the universe could look much smaller than it was. Andromeda sat at the centre of that illusion. It looked like a minor feature because its immensity was hidden along the line of sight. It looked near because there was no visual language for how far away it actually was. It looked quiet because the combined light of its stars had been diluted by space into a gentle blur. In hindsight, the mistake is easy to recognize, but inside the history itself it was almost unavoidable. The observers were not failing to see Andromeda. They were seeing it as fully as their tools and concepts allowed. What they lacked was not attention, but scale. The faint patch had to wait for new instruments, new measuring techniques, and a new willingness to let the universe grow beyond the Milky Way. Until then, it remained suspended between recognition and misunderstanding, recorded as a cloud, catalogued as a comet-like object that did not move, and absorbed into a cosmic map that made room for it only by making it smaller than it really was. That is the first unsettling truth in the story of Andromeda's distance. The nearest major galaxy did not begin as a distant world in human thought. It began as something local, uncertain, and easy to misplace. Its light was already carrying the evidence of a universe larger than the Milky Way, but the evidence had not yet become readable. And so, for nearly 1,000 years after Al-Sufi's careful note, the great galaxy next door remained hidden in plain sight, not because it was dark, but because the mind had not yet learned how large a faint smudge could be. The argument over Andromeda became unavoidable when astronomy reached the point where the old labels no longer carried enough weight. By the early 20th century, spiral nebulae had become some of the most important unresolved objects in the sky. They were not rare, and they were not visually random. Many showed a central concentration with curved arms extending outward, a pattern too organized to dismiss as accidental haze. Yet the meaning of that pattern remained uncertain. If the spirals were inside the Milky Way, then the Milky Way had to contain not only stars and gas, but also large rotating systems of luminous material whose true physical nature was still unclear. If the spirals lay outside it, then the Milky Way was only one galaxy among many, and the scale of the universe had been underestimated by a degree that would change nearly every cosmic map. The problem was not that astronomers lacked opinions. The problem was that the same observations could be arranged into different explanations. A spiral nebula could look like a forming system inside our galaxy, or like a distant system beyond it. Without a secure distance, the debate could not be closed. This uncertainty came to a public focus in April of 1920, when Harlow Shapley and Heber Curtis presented opposing views at the Smithsonian Institution in Washington. The event later became known as the Great Debate, though its importance was not that one speaker won and the other lost in a simple way. Its importance was that astronomy had reached a threshold where the size of the universe itself was under formal dispute. Shapley argued from a Milky Way larger than many astronomers had previously imagined. His work on globular clusters suggested that the Sun was not near the centre of the galaxy, and that the stellar system around us was vast. In that larger Milky Way, there seemed to be room for the spiral nebulae as internal objects. This view preserved a universe dominated by one great galactic structure, with the spirals still placed within it. Curtis defended the more radical interpretation. He argued that the spiral nebulae were island universes, separate stellar systems at immense distances. His evidence was not perfect, but it was suggestive. Explosions observed in Andromeda appeared faint when compared with similar events elsewhere, and faintness can point toward distance when the intrinsic brightness of the event is roughly understood. Dark lanes visible in some spirals also resembled dust structures in large stellar systems seen from different angles. These clues implied that the spirals were not nearby gas clouds, but enormous systems viewed from far away. Curtis did not yet have the final measurement, and some of his estimates were too small by modern standards, but his central direction was closer to the truth. The debate remained unsettled because both sides carried strengths and weaknesses. Shapley had helped reveal that the Milky Way was much larger and more structured than the old star-centered picture allowed, but his distance scale made it easier to keep the spirals inside our galaxy. Curtis saw the extragalactic nature of the spirals more clearly, but the available evidence still depended on interpretation. What the debate exposed was a deeper limitation. Astronomy could describe the sky with growing precision, but the universe could not be properly understood until distance became measurable across truly cosmic scales. The eye could not do this. Ordinary telescopic appearance could not do this. Even careful comparison of brightness had to be tied to objects whose true luminosity was known. Andromeda required a standard candle, a type of object whose real brightness could be inferred independently. The essential tool had already been found, though its full force was still unfolding. Henrietta Swan Leavitt, studying variable stars in the Magellanic Clouds, had discovered a relationship between the pulsation period of Cepheid variables and their intrinsic luminosity. A Cepheid is a star that brightens and dims in a regular cycle, because its outer layers expand and contract. Leavitt found that the longer the cycle, the brighter the star truly is. This relationship changed astronomy because it turned rhythm into distance. Once the period of a Cepheid was measured, its true brightness could be estimated. Once true brightness was known, astronomers could compare it with the star's apparent brightness as seen from Earth. The difference revealed how far away the star must be. It was a careful method, built from repeated observation rather than speculation, and it gave astronomers a ladder strong enough to reach beyond the familiar star field. Andromeda became decisive when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson to resolve individual stars in the nebula. The instrument was the most powerful optical telescope of its time, and it allowed Hubble to examine Andromeda with a clarity earlier observers did not have. At first, the achievement itself was already significant. If individual stars could be separated inside the object, then Andromeda was no mere smooth cloud. It contained stellar points, and among them, Hubble identified Cepheid variables. That identification gave the debate exactly what it lacked. The question no longer depended mainly on whether the spiral shape looked local or distant. It could be tested by measuring a star whose light curve carried distance information. Hubble measured the changing brightness of Cepheids in Andromeda, applied the period luminosity relation, and found that the object lay far beyond the known bounds of the Milky Way. The exact value would later be refined, but the conclusion did not depend on perfect modern precision. Andromeda was not inside our galaxy. It was a separate galaxy. The old universe had not merely grown at the edges, it had changed category. The Milky Way, once treated by many as the main container of all visible reality, became one stellar system among others. This was a quiet kind of scientific rupture. No explosion appeared in the sky. No new object became visible to the unaided eye. The same faint smudge remained where it had always been, yet its meaning changed completely. Before Hubble's measurement, Andromeda could still be imagined as part of the Milky Way by those who accepted a sufficiently large galactic model. After the Cepheids were measured, that interpretation could no longer hold. A distance had entered the argument, and distance altered everything. The universe now had depth beyond the Milky Way. Other spiral nebulae could be understood as galaxies in their own right. The night sky was no longer a single system decorated with strange clouds, but a view into a cosmos populated by many large stellar systems, each separated from the others by spaces that earlier astronomy had barely begun to imagine. What makes this turning point so important is that it did not simply add one more object to a catalogue, it changed the status of all galaxies. Andromeda became the first clear proof that the Milky Way had peers. It was not an appendage of our galaxy, not a mist inside it, not a local swirl waiting to condense. It was a system with its own stars, structure, and history. The term island universe, once speculative, became a description of physical reality. The consequences widened quickly. If Andromeda was external, then many other spiral nebulae were likely external as well. The visible universe, formally compressed into one stellar system, opened into a distribution of galaxies. The number of known galaxies would rise as instruments improved, from nearby systems to distant clusters, then to deep fields filled with thousands of galaxies in small areas of sky. But the first decisive break came through Andromeda, because it was close enough to be studied and far enough to prove the old scale wrong. It stood at the boundary between the universe humans thought they inhabited and the universe measurement forced them to accept. There is a restraint in this discovery that is easy to miss. Hubble did not need Andromeda to look dramatic. He needed it to contain a measurable star. The distance was not revealed through appearance alone, but through a repeating pattern of light from a Cepheid variable. A star brightened, dimmed, brightened again, and in that rhythm the scale of the universe changed. The result was not only larger numbers, it was a new relationship between humanity and the sky. Andromeda had been visible for centuries, but visibility had not meant understanding. The object had been present in human sight long before the mind had the method to place it correctly. Once that method arrived, the familiar blur became evidence of a universe in which nearness is not what it seems. Andromeda was the closest great example of something fundamentally unreachable by ordinary human scale. Yet it was also close enough for its stars to become measurable. That combination gave it a unique role. It was both accessible to observation and inaccessible to travel, both familiar in the sky and separate from the world of familiar distances. The universe doubled first in principle, from one galaxy to more than one, and then expanded beyond easy comprehension as the same logic was applied across the sky. Andromeda was not the final answer. It was the first stable doorway. Once its distance was measured, the question changed from whether other galaxies existed to how large, how numerous, and how remote they were. The small cloud had become a galaxy, and the galaxy had become a measuring point for a much larger cosmos. What ended in that realization was not curiosity, but the last serious version of a small universe. Andromeda becomes harder to misunderstand once it is treated not as a faint patch of light, but as a complete physical system. The object that entered early catalogues as a cloud is now known to be a large spiral galaxy, shaped by gravity, rotation, star formation, dark matter, and a long history of encounters with smaller systems. It is not a loose swarm of stars moving in the same general direction. It is an organized structure, with a dense central region, a broad stellar disk, long spiral arms, dust lanes, gas clouds, clusters, remnants of older stars, and a surrounding population of smaller satellite galaxies. Its visible form is often described as a barred spiral, meaning that the central concentration is not simply round, but includes an elongated bar of stars through the inner region, with spiral structure extending outward from that central arrangement. This detail matters because it makes Andromeda less like an isolated glowing object and more like a working galaxy, a system with internal motion and a record of change. Every major feature is connected to something physical. The central brightness comes from older, densely packed stars. The darker lanes are regions where dust blocks and reddened starlight. The bluer portions of the arms point toward areas where younger, hotter stars have formed. The galaxy is not only shining, It is carrying its history and its structure across its full extent. Andromeda spans roughly 200,000 light-years, making it larger in diameter than the Milky Way's bright stellar disk as it is usually described. That number should be handled carefully, because a galaxy does not have a sharp solid edge. Its stars thin gradually into a wider halo, and its dark matter reaches farther still. Even so, the scale of the visible disk is enough to change the way the object is understood. Light itself would need about 200,000 years to cross Andromeda from one side to the other. That is only the width of the galaxy, not the distance from Earth to it. Within that span are roughly 1 trillion stars, though any exact count depends on how faint a star can be included and how the total mass is modelled. Many of those stars are small red dwarfs, dim and long-lived, too faint to be individually seen from such a distance with ordinary observations. Others are sun-like stars, red giants, hot blue stars, white dwarfs, neutron stars, and stellar remnants. A galaxy is not one kind of object repeated many times. It is a population with age, chemistry, motion, and memory distributed through it. Andromeda contains stars born in quiet regions, stars formed in disturbed gas after gravitational encounters, stars stripped from smaller galaxies, and stars that belong to older populations whose motions preserve traces of events that happened billions of years ago. At its centre lies a supermassive black hole, with a mass estimated in the range of roughly 100 million to 200 million suns. The exact value remains a matter of measurement and modelling, but the important comparison is clear. The black hole at the centre of the Milky Way, Sagittarius A star, is far smaller, with a mass of about 4 million suns. Andromeda's central black hole therefore belongs to a different scale within the nearby universe. It does not define the whole galaxy by itself, and it is not swallowing Andromeda in any simple sense. Its influence is strongest in the central region, where the motions of nearby stars reveal the presence of a compact mass. Around it, the galaxy continues as a broader gravitational system, held together not only by visible matter but by a much larger dark matter halo, whose full extent cannot be seen directly. The black hole is important because it shows that Andromeda has a deep central structure. But the galaxy is not just a central object with stars around it, it is a layered system, and each layer tells a different part of the story. The disk records ongoing and past star formation. The bulge preserves older stellar populations. The halo contains diffuse stars and streams, many of them likely left by smaller galaxies that Andromeda pulled apart. These stellar streams are especially useful because they show that a galaxy is not built all at once and then left unchanged. It grows by absorbing other systems. Gravity stretches those smaller systems into long arcs and faint ribbons of stars, leaving evidence that can remain visible long after the original galaxy has lost its shape. Andromeda's surroundings make this even clearer. It is the dominant member of its own local family, with satellite galaxies moving around it under its gravity. Among the best known are Messier 32 and Messier 110, compact companions visible with modest telescopes under suitable conditions. Around them is a larger collection of fainter dwarf galaxies, some difficult to detect because they contain relatively few stars spread across wide areas. These small systems matter because they help reveal the mass and history of Andromeda. Their orbits, positions, and stellar populations carry information about how the larger galaxy has grown and how gravity has arranged the local environment. The Milky Way has its own satellites, and together the Milky Way and Andromeda dominate what astronomers call the local group, a collection of galaxies spread across several million light-years. Most members of this group are dwarfs, faint systems containing far fewer stars than either of the two large spirals. In that setting, Andromeda is not merely a neighbour, It is one of the two main gravitational anchors of the region. That role helps explain why it is so valuable to study. The Milky Way is home, but being inside it creates a serious observational problem. Dust in the galactic plane blocks parts of the view, and the Sun's position within the disk makes it difficult to see the whole structure at once. Andromeda offers a different advantage. It is similar enough to the Milky Way to serve as a comparison, yet distant enough to be observed as a complete galaxy from outside. Its disk, bulge, halo, companions, and streams can be mapped across the sky. This does not make the work simple. Its stars are still separated from Earth by about 2.5 million light-years, and many are too faint to isolate. But the overall system can be studied in a way that the Milky Way cannot be studied from within. Large surveys with space telescopes and ground-based observatories have made Andromeda increasingly detailed. High-resolution imaging has resolved enormous numbers of individual stars in its disk, allowing astronomers to compare ages and chemical compositions across different regions. Those measurements show that the galaxy is not smooth in its history. Some regions hold older, quieter populations. Others show evidence of more recent star formation. The distribution of stars and streams suggests that Andromeda has experienced major interactions, including the absorption of smaller galaxies and possibly a large merger in its past. Such events would have disturbed its disk, driven gas inward, triggered new star formation, and left patterns that can still be detected. The galaxy therefore carries two impressions at once. From Earth, it looks still and faint. In physical reality, it is the result of long gravitational processes, repeated encounters, and internal evolution across billions of years. This distinction is central to understanding why the distance is so severe. The farther Andromeda becomes from a mere blur, the more real its contents become. It has a central black hole with measurable influence. It has spiral arms where stars are born. It has satellites that orbit and sometimes dissolve. It has stellar populations old enough to preserve ancient episodes of formation and disruption. It has a halo extending beyond the bright disk, containing material that does not fit neatly into the visible spiral shape. It is not a single destination, but a vast environment, with enough internal variety to occupy generations of study. Yet all of this detail arrives only through light, and that light has already spent millions of years crossing the gap. The better Andromeda is known, the less it feels like an abstract, distant object, and the more clearly the separation asserts itself. A telescope can turn the faint haze into maps, star counts, colour measurements, and models of motion. It can show the galaxy as a structured system rather than a soft patch in the sky. But no observation shortens the path. The increase in knowledge does not make Andromeda closer. It only makes the distance more precise and more difficult to dismiss. 1 trillion stars become not a poetic idea, but a population. A central black hole becomes not a dramatic centre, but a measured mass. A satellite galaxy becomes not an ornament, but a gravitational companion. The more each part is understood, the more the word neighbour begins to strain under its ordinary meaning. Andromeda is nearby only in the language of galaxies. By any scale connected to travel, communication, or lived time, it remains almost completely beyond reach. That is why this stage of the story matters before the distance is measured outward from Earth. The object across the void must first be made real. The faint light belongs to a full galaxy with structure, mass, and history. And only then does the separation between here and there take on its full weight. A useful way to approach Andromeda is not to begin with the galaxy itself, but with distances that already strain ordinary experience. The Moon is the first step because it is the only world beyond Earth where human beings have stood. Its average distance is about 239,000 miles. close enough for light to cross in a little more than 1 second, and close enough for the Apollo missions to reach in about 3 days. That achievement remains immense in human history. Yet on an astronomical scale, it belongs to the immediate neighbourhood of Earth. The Moon is not close because the journey is easy. It is close because the rest of space changes the meaning of far. The Sun gives the next measure. It lies about 93 million miles from Earth, and sunlight needs a little over 8 minutes to arrive. That delay is small enough to feel almost immediate, but it already shows that space cannot be understood by appearance alone. The Sun looks present in the sky, yet every sunrise is seen slightly after the light has left the solar surface. A spacecraft travelling at the speed of ordinary vehicles would need longer than a human lifetime to cover that separation. Probes can do better, and the Parker Solar Probe has moved closer to the Sun than any previous spacecraft while reaching speeds of hundreds of thousands of miles per hour. It is among the fastest objects ever made by human hands. Even so, that speed gains meaning only when placed against the distances beyond the inner solar system. Mars can come tens of millions of miles from Earth at favourable alignments, and robotic missions still require months to arrive. Jupiter is hundreds of millions of miles away at its closest, and missions sent there have needed years of careful trajectory work, gravity assists, and long cruise phases. Saturn is farther still, not only another planet in the sky, but a destination requiring a journey across much of the planetary system. These crossings are possible, but they are not casual. They use the motion of planets, the timing of launch windows, and the patience of mission teams who build machines expected to operate for years before reaching their main target. In this region, distance remains an engineering problem. It is severe, but it can be negotiated by propulsion, planning, and time. The outer solar system begins to change that feeling. Beyond Neptune, the Sun still dominates gravity, but its light has weakened, and the planets give way to smaller icy bodies, scattered objects, and the long uncertain edge of the Sun's influence. Far beyond the planets, the Oort cloud is thought to form a broad shell of icy bodies surrounding the solar system. Its outer regions may extend to roughly a light year or more from the Sun, though the exact boundary is not a hard surface and has never been directly observed. This is still the Sun's distant territory, but it is already beyond any human-made spacecraft. Voyager 1, launched in the late 1970s, is the most distant operating probe sent from Earth. It has crossed the heliopause, the region where the solar wind gives way to the interstellar medium, and it continues outward. Its achievement is extraordinary, yet after nearly half a century of travel it has covered only a tiny fraction of the distance to the outer Oort cloud. This is the first serious correction to intuition. Leaving the planets is not the same as leaving the solar system in any full gravitational sense. A probe can pass beyond the solar wind and still remain very close to home compared with the Sun's widest reach. The nearest stars bring a larger change. Proxima Centauri, part of the Alpha Centauri system, lies a little more than 4 light-years away. Light needs more than 4 years to make the crossing, and light is the fastest known messenger in nature. This means that even in the most favourable possible case, with no acceleration time and no slowing down, the nearest star cannot be reached in less than several years. Real spacecraft are far slower. At Voyager 1's speed, a crossing to Proxima Centauri would take tens of thousands of years if the probe were travelling in the correct direction. At the peak speed reached by Parker Solar Probe near the Sun, the same journey would still require thousands of years. Such comparisons are not meant to dismiss future engineering. They clarify the size of the gap between present machines and interstellar distance. The nearest star is not just farther than the planets. It belongs to a different class of distance, one in which civilizations, languages, and entire historical periods become small units of comparison. Yet Proxima Centauri is the favourable example. It is the closest known star beyond the Sun. Most stars in the Milky Way are much farther away, and the galaxy itself is wider than any direct experience can usefully contain. The bright stellar disk of the Milky Way spans on the order of 100,000 light-years. Light would need about 100,000 years to cross it from side to side. That figure is already larger than the span of recorded civilization by a wide margin. At the fastest speeds reached by human spacecraft, crossing the galaxy would not be a project of centuries or millennia, but of geological time. The journey would last longer than many major chapters in the history of life on Earth. This is still only the home galaxy. It contains the Sun, the planets, the visible band of the Milky Way, star-forming regions, stellar clusters, and the central bulge hidden partly by dust from Earth's position inside the disk. If a galaxy of this width already overwhelms travel, then the distance to Andromeda introduces a still larger separation. Andromeda lies about 2.5 million light-years from the Milky Way. Compared with the width of the Milky Way's disk, that distance is roughly 25 times larger. The nearest major galaxy is not located just outside the edge of our own. It is separated by many galactic widths of space. This comparison is more useful than a single number, because it places Andromeda against a structure that is itself enormous. The Milky Way is large enough for light to spend 100,000 years crossing it, and the gap to Andromeda is many times that span. The mind can say the number, but the physical meaning requires this sequence. Earth to Moon is days by crude spacecraft. Earth to Sun is minutes by light. Earth to Mars is months by robotic mission. Earth to the outer planets is years. The Sun to the nearest star is years by light, and tens of thousands of years by existing spacecraft. Across the Milky Way is 100,000 years by light. Then Andromeda waits beyond that, at a distance measured in millions of light-years. Each step does not merely add more space. It changes the type of problem being faced. Inside the solar system, spacecraft can be tracked, guided, and corrected within mission lifetimes. Across interstellar space, even the nearest destination exceeds normal historical planning. Across a galaxy, the crossing becomes tied to deep time. Between galaxies, the idea of a journey loses almost every ordinary reference point. A machine could travel outward for an age longer than the existence of human civilization, and still remain, in cosmic terms, near its place of origin. This is why Andromeda is so difficult to place emotionally. It is called nearby because astronomy uses categories shaped by enormous scales among large galaxies. Andromeda is close. It is part of the same local group and is gravitationally bound to the Milky Way. Its light is bright enough to be visible under dark skies, and modern instruments can resolve many of its stars. By observational standards, it is accessible by travel standards. It is beyond any realistic continuity of human time. The same object can be both near and unreachable depending on which scale is being used. The phrase nearest major galaxy is therefore accurate but incomplete. It describes Andromeda's rank among galaxies, not its relationship to human movement. The distance becomes clearer only after the smaller distances have been allowed to fail one by one. The Moon is close enough to visit. Mars is difficult but reachable by machines. The outer planets are remote but within the range of long missions. The edge of the solar system is already almost beyond practical return. The nearest star moves into durations longer than cultures last. The galaxy extends into spans that resemble the timing of evolution rather than exploration. Andromeda stands beyond even that, not as a final point on a map, but as the first great example of intergalactic separation. Its faint light makes it visible, yet visibility should not be confused with nearness. The scale sequence ends with a quiet correction to ordinary language. The galaxy next door is next door only to another galaxy, for anything moving from Earth. The gap is so large that even the fastest human-made speeds leave it effectively untouched. Andromeda's distance can be measured in light years, but a light year is not only a unit of length, it is also a record of travel time. The light that reaches Earth from Andromeda has been moving through space for about 2.5 million years before it enters a telescope, a camera sensor, or a human eye. That statement is simple, but its meaning is difficult to hold steadily. It means that Andromeda is never seen as it is in the present moment. It is seen as it was when the light began the crossing, long before written history, long before agriculture, long before any city, and before Homo sapiens had fully emerged as the only surviving human species on Earth. The galaxy has continued to change during those millions of years. Stars have moved in their orbits. Some massive stars have died. New stars have formed in gas clouds. Smaller systems have continued to fall through its halo. None of those recent changes are visible from Earth yet. They are still in transit, carried by light that has not arrived. The image in the sky is therefore not only distant, it is old. Every observation of Andromeda is an observation of a past state, preserved by the speed limit of nature. This is true for all astronomy beyond Earth. But Andromeda makes the fact unusually clear because it is close enough to be visible, and far enough that the delay reaches into deep human ancestry. The Moon is seen a little more than 1 second in the past. The Sun is seen a little more than 8 minutes in the past. Nearby stars are seen years or decades in the past. Andromeda is seen millions of years in the past. The same act of looking upward joins ordinary vision to geological time. When the photons now arriving from Andromeda left their source, Earth was entering a colder and more unstable phase of its recent history. Ice sheets were expanding and retreating across parts of the northern hemisphere. Ocean levels shifted as water became locked in ice and then returned to the seas. Climates moved in long pulses, reshaping habitats and migration routes. The continents had nearly the forms recognized today, but the living world was arranged differently. Large mammals moved through landscapes that would later lose many of their most distinctive animals. Mastodons, early horses, giant ground sloths, saber-toothed cats, and many other creatures occupied environments that no longer exist in the same form. The Isthmus of Panama had closed in the geologically recent past, linking North and South America and allowing animals to move between continents in a major biological exchange. While these changes unfolded on Earth, the light from Andromeda was already crossing the space between galaxies, not waiting for life here to become capable of noticing it. In Africa, early members of the genus Homo were part of that same world. Stone tools had begun to appear in the archaeological record, simple but important evidence that hands, attention, and changing brains were shaping material in repeatable ways. These toolmakers did not know the stars as physical suns. They did not know galaxies. They did not have mathematics, writing, or instruments. Yet the light that would one day be interpreted by astronomers had already begun its journey. This contrast is not useful because it makes the past seem primitive. It is useful because it restores proportion. The entire development from early stone tools to observatories capable of resolving stars in another galaxy fits inside the travel time of one beam of light. During that crossing, human evolution passed through many stages. Populations changed, bodies changed, brains enlarged, species appeared and disappeared. Fire became a controlled tool. Language emerged, though its early history leaves only indirect traces. Groups moved across continents. Coastlines changed. Ice advanced and withdrew. By the time agriculture began, the light from Andromeda had almost completed its journey by cosmic standards. By the time the first cities formed, the crossing was already in its final brief fraction. By the time astronomers began recording the small cloud in the sky, the light had been travelling for nearly the entire span. This is what makes the distance different from a large number on a page. It contains almost the whole recognisable story of humanity. The delay also changes the idea of present reality. Andromeda exists now, but its now is not directly available from Earth. The present state of that galaxy is separated from observation by the same interval that separates the observer from the early Pleistocene world. There is no practical way to remove this delay because it is not caused by weak instruments or poor technique. It is caused by the finite speed of light. Better telescopes can sharpen the view, detect fainter stars, analyze spectra with more precision, and reveal structure across the disk and halo. But they cannot make the incoming light younger. A perfect telescope would still see the Andromeda of 2.5 million years ago. This is one of the quiet limits built into astronomy. The more distant the object, the older the information. The universe is not displayed all at once in a single shared present. It is layered by travel time. Looking outward means looking backward, and Andromeda is the nearest major example of how deep that backward view can become, while still seeming familiar to the naked eye. The fact also clarifies why distance and time cannot be separated at cosmic scales. On Earth, they usually feel different. A distant mountain may be seen as it is almost now. A city across an ocean may be contacted in a fraction of a second by radio signals and fibre optic cables. Human technology has made the planet feel nearly simultaneous. Space does not behave that way. A message sent to the moon returns quickly enough for conversation. A signal sent to Mars may take minutes, depending on where the planets are. A signal sent to the outer solar system takes hours. A signal sent to the nearest star takes years. A signal sent to Andromeda takes about 2.5 million years in one direction. The distance is therefore not simply an amount of space to be crossed. It is an interval imposed on all information. Nothing known can carry news faster. If a bright event occurred in Andromeda at this moment, Earth would not know for millions of years. If a star there ended its life, if a cluster was disturbed, if a compact object flared, the event would belong to Andromeda's present, but not to Earth's observable sky. For Earth, it would not yet have happened in any measurable sense. Such delays do not make astronomy unreliable. They define what astronomy measures. The past is not a defect in the image. It is the image. Andromeda's old light allows the galaxy to be studied at a specific moment in its history, while the present remains beyond immediate reach. In that way, every astronomical observation is both evidence and limitation. It gives information, but also states how late that information is. The more carefully the distance is known, the more clearly the delay can be understood. 2.5 million years is not only how far the light has travelled, it is how long Andromeda has been absent from direct present tense knowledge. This can make the galaxy feel less like a neighbouring place, and more like a preserved message from a previous Earth. The message was not sent deliberately. It is simply radiation moving outward from stars, dust and gas. But it arrives carrying an accidental archive. It crossed space while ice ages reshaped continents, while early humans learned to live with fire, while modern humans spread, while languages formed and vanished without record, while animals that once dominated entire regions disappeared, while agriculture reorganized landscapes, while the first astronomers named the stars, and while telescopes turned the small cloud into a galaxy. All of that history occurred during the light's passage, and only at the end of it did the signal become part of human knowledge. This is the calm but severe meaning of Andromeda's distance. It is not only far away in space, It is offset from human experience by a duration longer than the age of the species that can study it. The galaxy is close enough for its light to enter the eye unaided, yet the journey of that light began in a world no human being would recognize. The observation feels immediate because vision always feels immediate. The science shows that it is not. Andromeda's faint glow is the arrival of ancient information, and every photon completes a crossing that began before humanity had a name, a memory, or a sky understood as a universe. The delay in Andromeda's light also changes something simpler than travel. It changes the meaning of communication. A spacecraft crossing the gap is easy to recognize as an almost impossible project because it requires matter, energy, shielding, navigation, and survival across timescales far beyond any mission ever built. A message seems lighter. It needs no life support, no stored food, no engine that burns for ages, and no structure strong enough to endure dust impacts over intergalactic distance. A radio signal can leave Earth at the speed of light, spreading outward as an electromagnetic wave. In ordinary thinking, that makes communication feel more hopeful than travel. Light is the fastest carrier known to physics, and radio is one of the ways intelligence has learned to shape light into information. Yet the distance to Andromeda removes even this easier form of contact from the scale where conversation has meaning. A signal sent from Earth toward Andromeda would require about 2.5 million years to arrive. That is only the outward leg. If a receiver in Andromeda detected it, understood that it was artificial, decoded its structure, and sent back a reply by the same fastest possible means, the return signal would require another 2.5 million years. One exchange would take about 5 million years. The problem is not simply that this is a long time. The problem is that the sender and receiver cannot reasonably be treated as the same continuous participants across that duration. 5 million years reaches beyond recorded history, beyond the age of agriculture, beyond the presence of Homo sapiens, and back toward the early branching of the human lineage from other apes. A message sent by beings that distant in the past would arrive in a world transformed not merely in language or politics, but in biology. The descendants who received an answer would not share the same bodies, the same institutions, the same assumptions, or perhaps even the same planet in a stable form. At that scale, a reply is no longer a reply in the human sense. It is an event separated from its cause by so much intervening change that continuity becomes a fragile idea. Conversation depends on more than the transfer of information. It depends on the persistence of context. A question must survive long enough for the answer to matter. The beings who ask must either remain present or leave institutions capable of preserving the question with enough fidelity that the response can still be understood. On Earth, this has already proved difficult over far shorter spans. Languages change within centuries. Scripts are forgotten. Monuments lose their meanings. Civilizations preserve some records and fail to preserve others. Even durable objects become ambiguous when the culture that made them is gone. Written history covers only a few thousand years. And within that short interval, many voices have already become partial, damaged, or silent. Andromeda stretches the delay by hundreds of times beyond the oldest living records of civilization. A message sent there would need to carry not only content, but a defense against extinction, translation failure, cultural loss, planetary change, and the simple fact that no society has ever demonstrated continuity across anything like the required interval. The mathematics of the round trip turns communication into archaeology before it begins. The outgoing signal would be a fossil of the civilization that created it. The returning signal, if one ever came, would be received by descendants who would have to reconstruct not only the sender's question, but the entire reason the answer was expected. That does not make such a signal physically impossible. It makes its meaning unstable. The difference matters. Physics allows electromagnetic radiation to cross the distance. It does not allow the exchange to remain socially intact. A civilization could choose to transmit a beacon toward Andromeda, perhaps as a declaration of existence, a scientific archive, or a symbolic act. The signal would move outward faithfully at light speed. It might eventually pass through the outskirts of the galaxy and wash across any receiving instrument in its path. But the act would be more like placing a record into deep time than beginning a dialogue. The sender could not expect a response within the lifespan of any individual, nation, species, or technological tradition now known. The message would leave the present and enter a duration where ordinary responsibility becomes hard to define. It would be sent by one version of Earth and arrive, if noticed at all, in another galaxy during a later chapter of both systems. The same condition applies in reverse. Any signal arriving from Andromeda today would have been transmitted 2.5 million years ago. If it were artificial, it would not reveal the current state of the civilization that sent it. It would reveal only that, in Andromeda's past, some source shaped radiation into information. The senders might still exist. They might have changed beyond recognition. They might have vanished before Homo sapiens appeared. The signal would be valuable beyond measure, but it would not solve the problem of present contact. It would be evidence from deep time, not a call in progress. Even the discovery of intelligence across that distance would arrive as history. The receiving civilization on Earth would learn that something had once existed, not that it could be reached in any practical or mutual sense. That distinction removes much of the familiar drama from intergalactic contact and replaces it with a quieter limitation. The universe may contain minds beyond the Milky Way, but the scale between galaxies makes shared time difficult to preserve. Awareness could cross the gap as delayed radiation. Relationship could not easily follow. This is not caused by a lack of imagination. It is caused by the speed of causality, the limit at which influence can move from one place to another. In daily life, communication feels nearly instant because the planet is small compared with the light speed. Signals move around Earth so quickly that delay often disappears beneath human perception. Even contact with spacecraft near Mars, though delayed by minutes, still allows mission control to plan, correct, and respond within a recognizable operational frame. The outer planets stretch delay into hours, but the exchange remains humanly meaningful. Andromeda breaks that frame entirely. The signal does not return after a pause, a generation, or an era. It returns after evolution has had time to alter the species that began the exchange. The effect is not merely slow communication. It is the collapse of the shared present. Two worlds separated by Andromeda's distance do not inhabit the same practical now, even though both exist within the same universe. Each sees the other through ancient light. Each can act, but the knowledge of that action arrives after a span large enough to absorb most of what would make the action recognizable. The most careful message design cannot remove this problem. A civilization could encode mathematics, images, chemical information, star maps, or descriptions of its biology. It could build redundancy into the signal and repeat it for centuries. It could use powerful transmitters and choose frequencies likely to cross space with minimal absorption. These choices might improve the chance of detection and understanding. They would not improve the delay. The content can be protected, but not hurried. A perfectly designed message still arrives millions of years late by the standards of the society that sent it. The reply, if it comes, answers a past so remote that the original communicators have become part of their planet's fossil and archaeological record. In this sense, Andromeda's distance is a boundary around dialogue. It permits observation and perhaps one-way announcement, but it denies exchange as humans normally understand it. It turns communication into a chain of isolated deposits, each one thrown across a gulf and received by a future that cannot be predicted. This is why the idea of sending a message to the nearest major galaxy is more severe than it first appears. The difficulty is not only finding someone there, or building a transmitter strong enough, or agreeing on a code. Those are hard problems, but they belong to engineering and interpretation. The deeper obstacle is continuity. The universe allows information to travel, but it does not guarantee that meaning survives the interval between departure and arrival. Andromeda shows this with unusual clarity because it is near enough to imagine and far enough to defeat mutual presence. Its light already proves that radiation can cross the gap. Its delay proves that crossing is not the same as connection. A photon can make the journey. A sentence may make the journey. A civilization's intention may not. By the time an answer could return, the question would belong to a world that no longer exists in the same form, and the conversation would have become a record of separated moments rather than a shared act between living societies. The space between the Milky Way and Andromeda is not empty in the ordinary sense of the word. It is not empty like an abandoned room, a quiet road, or the dark interval between two visible stars. It is a physical environment with matter, radiation, gravity, and fields. But almost all of those things are present at densities so low that ordinary experience gives no useful comparison. Inside a galaxy, space already appears nearly vacant. The Sun is separated from the nearest star system by more than 4 light-years. The space between stars contains thin gas, dust, charged particles, cosmic rays, and magnetic fields. But even there, the amount of material is extremely small. A typical region of the interstellar medium may contain around 1 atom in a cubic centimetre, sometimes more in clouds and sometimes far less in hot diffuse regions. That is a far better vacuum than anything needed for most experiments on Earth. Yet it is still rich compared with the environment between galaxies. In the intergalactic medium of the local group, the density can fall to only a few atoms in a cubic metre, with large uncertainty from place to place. That difference matters because it changes the physical character of the crossing. A spacecraft moving through interstellar space still remains inside the broad structure of a galaxy. It moves through a region shaped by stars, supernova remnants, dust, gas clouds, radiation fields, and a magnetic environment connected to the galactic disk and halo. Once it leaves the Milky Way for the space toward Andromeda, even those weak forms of structure become thinner and less helpful. The surroundings do not become absolutely nothing, because absolute nothing is not a condition found in the real universe. There is still the cosmic microwave background, the faint afterglow of the early universe. There are still rare particles, diffuse plasma, distant photons from galaxies, and the gravitational influence of the local group. But for any traveller or instrument, the environment would be defined mainly by absence. There would be no nearby stars to pass in any regular way. There would be no planetary systems as useful reference points. There would be no bright nebulae, no open clusters, no dense star fields, and no familiar pattern of local objects by which progress could feel anchored. Position would have to be calculated through instruments, timing, and remote observations rather than through any nearby landmark. The Milky Way would remain behind as a large source of light and gravity, but it would gradually lose its immediate dominance. Ahead, Andromeda would slowly strengthen as a target, though only over spans of time far longer than any human life. The region between them is part of the local group, so it is not empty of all galaxies. Several dwarf galaxies occupy the wider space around the 2 large spirals, and some lie in directions that make the area between the Milky Way and Andromeda more complicated than a simple gap. These dwarfs are real galaxies, with stars, dark matter, and histories of their own. Some are bound more clearly to the Milky Way, some to Andromeda, and some are more loosely placed within the group. Their presence is important scientifically because they help trace the gravitational structure of the local group and preserve clues about how larger galaxies grow. Yet their existence does not make intergalactic space dense or navigable in the ordinary sense. Most of the volume between the two giants remains without star systems nearby. A dwarf galaxy may contain millions or billions of stars, but it occupies an extremely small fraction of the available space. Its influence does not fill the surrounding void with accessible stepping stones. It simply shows that the local group is a gravitational family rather than a clean pair of isolated objects. The difference between volume and contents is central here. Galaxies are enormous, but the space around them is larger still. Stars and gas are gathered into islands of high density by cosmic standards, while the regions between those concentrations contain very little matter. This pattern comes from the way gravity builds structure. Matter in the early universe was not spread perfectly evenly. Slight density differences grew over time. Regions with more matter attracted still more matter, forming filaments, clusters, groups, and galaxies. Regions with less matter became emptier by comparison. The space between the Milky Way and Andromeda is not one of the largest cosmic voids, because it lies inside a bound group of galaxies, but it still belongs to the same broad principle. Matter has collected into galaxies, halos, and smaller companions, leaving most of the intervening volume extremely thin. For light, such emptiness is not a serious obstacle. Photons cross it constantly. The faint glow of Andromeda reaches Earth because space between the galaxies is transparent across many wavelengths, with little dust or gas to block the light. For matter, the same transparency has a different meaning. A physical craft would not find much to interact with, but that would not make the journey safe or simple. At very high speeds, even rare particles become significant over immense distances. A single atom striking a spacecraft at a large fraction of light speed would carry much more energy than the same atom at ordinary speeds. Dust grains, although extremely scarce, would be more dangerous still. Shielding against that hazard over millions of light years would be a major physical challenge. The void is therefore not a road cleared for travel. It is a region so thin that almost nothing can be used. While the little matter that is encountered may still matter at extreme velocity, this is one of the quiet contradictions of intergalactic distance. There is too little material for support, repair, refueling, or reference, yet enough material to create risk for anything moving fast enough to make the crossing less hopeless. The radiation environment would also be sparse but persistent. Cosmic rays, produced by energetic events across galaxies and intergalactic space, would continue to pass through the region. The cosmic microwave background would remain everywhere, nearly uniform, providing a cold bath of radiation from the early universe. Distant galaxies would contribute faint light across the sky. None of this would create a landscape. It would create a measurable background. Instruments could use that background for science, but not for comfort, orientation in the human sense, or any feeling of arrival. The main visible structures would be the galaxies themselves, shrinking behind or growing ahead across enormous intervals. The Milky Way, once departed from far enough, would become an external galaxy. Its disk and central regions seen from outside, Andromeda would remain the destination, but its apparent growth would be slow beyond ordinary recognition. The physical emptiness between them would make time feel even larger, because few local changes would mark it. In a planetary journey, the departure world recedes, the target grows, and the spacecraft passes through changing regions of solar influence. In a crossing to Andromeda, after the galactic halo thinned away, the environment would offer long periods in which very little nearby changed at all. That is not because motion has stopped. It is because the scale is too large for ordinary markers of motion to appear. The spacecraft could be moving at a speed beyond current engineering and still require ages before the view ahead looked meaningfully different. The void, therefore, has a scientific meaning and a psychological one, although the latter can only be inferred scientifically. It is a low-density medium shaped by the distribution of matter in the local group, transparent to much of the light that reveals Andromeda, and populated only sparsely by particles, fields, and smaller galaxies. Conceptually, it shows that the difficulty of Andromeda is not contained in the number of light-years alone. The distance is filled mostly with conditions that offer no natural support for crossing it. There is no chain of nearby stars linking the Milky Way to Andromeda. There is no continuous bridge of dense gas. There is no route that converts the problem into a sequence of manageable stops. There are gravitational relations across the local group, and there are faint streams and halos around galaxies, but these do not create an accessible path. They are evidence of structure on scales much larger than any traveller could easily use. This is why the word between becomes so important. Between Earth and the Moon there is space. But the endpoints remain close enough for mission control, communication, and return. Between planets there is more emptiness, but still a solar system with predictable bodies and usable gravity. Between stars there are long gaps, yet the destination is at least a single nearby sun. Between galaxies, the scale and the scarcity combine. Andromeda is visible because light has no need for supplies, rest, or shelter. Matter does. The space separating the two galaxies is therefore not a blank waiting to be crossed. It is a real environment whose defining fact is its extreme thinness, and that thinness reinforces the larger truth. The nearest major galaxy is not separated from the Milky Way by a crowded frontier, but by a vast, cold, low-density region where almost every ordinary meaning of travel loses the conditions that make it understandable. Motion across intergalactic space would not resemble the kind of travel that human experience teaches. On Earth, movement is recognized through changing surroundings. A road passes beneath a vehicle. A coastline shifts along the horizon. Clouds move overhead. Even in the solar system, a spacecraft can measure progress through the changing angle of the sun, the growing disk of a planet, the weakening of solar radiation, and the timing of radio signals. Intergalactic travel removes most of those signs. A craft leaving the Milky Way toward Andromeda would begin with familiar astronomical references, at least in a broad sense. The sun would become one star among many, then fade into the background of the galactic disk. The spiral structure of the Milky Way, impossible to see fully from within, would gradually become an external form behind the spacecraft. Star fields would thin, bright local objects would fall away, the halo of the galaxy, containing old stars, globular clusters. Dark matter and thin gas would stretch outward, but it would not provide anything like a continuous landscape. Eventually, the craft would enter a region where the main visible fact of its position was the shrinking galaxy behind it and the distant galaxy ahead. This is where motion begins to lose its ordinary meaning. Velocity can be high, instruments can record changing coordinates, and the path can be calculated with precision, but the view can remain almost unchanged for times longer than civilizations have existed. Even a spacecraft moving far faster than any present machine would require immense spans before Andromeda appeared noticeably larger to a human observer. The reason is simple. The target is not only far away, it is large enough that small changes in distance barely alter its apparent size across short intervals. A journey covering thousands of years might still leave the destination as a faint external galaxy, slightly brighter, slightly broader, but not transformed into a nearby world. The experience would be one of measured progress without visual reward. The craft would be moving, but the surroundings would not provide the constant evidence of movement that living minds use to understand travel. For most of the crossing, the endpoints would define the journey more than the path itself. Behind would be the Milky Way, containing the Sun, Earth, and every known origin of the mission. Ahead would be Andromeda, not yet a place of arrival but a distant structured light. Around the craft would be the sparse medium described by instruments rather than seen as scenery. The long duration would turn navigation into an act of persistence across almost unchanging conditions. This matters because many ideas about deep space travel are built around the image of crossing. Crossing suggests passage from one region into another, with stages, landmarks, and a growing sense of approach. Between galaxies, those stages become weak. There is a departure from the Milky Way's environment. Then a vast middle in which almost nothing local announces itself. Then, only after ages, an entrance into Andromeda's outer halo. The middle is not a short interval between meaningful places, it is nearly the whole journey. A mission could spend most of its existence in that middle state, belonging fully to neither galaxy. It would have left the dense stellar environment of its origin without yet entering the dense stellar environment of its destination. The nearest important objects would be remote systems rather than nearby bodies. The craft would be in the local group, but not in a region that gives travel a natural rhythm. This creates a practical problem as well as a conceptual one. Spacecraft missions usually depend on correction. They monitor position, adjust course, manage power, respond to faults, and use communication with Earth. Across the Andromeda's distance, ordinary mission control fails immediately as a continuous process. Signals to the craft would take longer and longer to arrive as it receded, until even instructions sent from Earth would be delayed by thousands, then hundreds of thousands, then millions of years. The craft would need to become autonomous in a sense beyond present engineering. It could not rely on human teams to guide it in real time or even in delayed operational cycles. The society that launched it would not remain available as an active partner through the crossing. Any machine attempting such a passage would have to carry its own long-term decision systems, repair capacities, stored knowledge, and ability to handle conditions that could not all be predicted when it departed. The distance would separate the mission not only from Earth as a place, but from Earth as an institution capable of support. Energy would be another quiet constraint. In the solar system, sunlight is a usable resource across large regions, though it weakens with distance. Beyond the outer planets, nuclear power becomes more important. Between galaxies, no nearby star can be counted on for energy. A craft would need internal sources designed to last across extraordinary time, or it would need a form of propulsion and power far beyond current capability. If it were moving slowly, the duration would be so great that material decay, radiation damage, impacts, and system failure would accumulate across ages. If it were moving very fast, the energy required to accelerate and shield it would rise sharply. High speed does not erase the environment, it changes how dangerous the environment becomes. Rare particles and dust become more energetic on impact. Navigation must account for small uncertainties magnified across huge distance. A tiny error in direction, almost meaningless near Earth, could grow into a miss by many light years at the destination. The path has to be accurate across a moving target as both galaxies orbit within the local group and continue their mutual approach. This does not make the laws of physics hostile in a dramatic sense. It simply means the distance converts every small requirement into a severe one. Guidance, power, shielding, memory, repair, and purpose all have to survive time rather than merely distance. The idea of passengers makes the problem still harder. A living crew would require a self-sustaining environment across durations far beyond any biological or cultural continuity ever observed. Generation ships are sometimes proposed for interstellar travel, where descendants of the original crew might arrive at a nearby star after centuries or millennia. The Andromeda distance stretches that concept until it loses definition. Millions of years aboard a closed system would not be a voyage in the social sense familiar from history. It would be an artificial world evolving in isolation, its inhabitants. If any persisted, would not simply be travellers waiting to arrive. They would become the main civilization, with the destination transformed into a remote inherited premise. Languages, bodies, customs, and goals could change many times before Andromeda became near. The original mission plan would be an archaeological object within the vessel's own history. Even advanced suspended animation, if assumed as a speculative technology, would still face the burden of preserving bodies, minds, and machines for intervals longer than many species endure. The gap would test not only engineering but identity. A probe avoids some of these difficulties because it does not need a society inside it. But even a probe cannot avoid the central fact that arrival would be detached from its origin. The data it might gather in Andromeda would be valuable only if it could transmit back, and that return signal would require another 2.5 million years to reach the Milky Way. By the time the information arrived, the world that built the probe would be long removed from its own starting point. Thus, even successful arrival would not create an ordinary exploration cycle. There would be no launch, arrival, report, and response within one coherent historical frame. There would be only deposits of information separated by millions of years. This is the difference between observation from Earth and physical travel. Light from Andromeda already arrives on its own. It gives access without motion. A spacecraft would try to reverse that relationship by sending matter across the same path. But matter carries the burdens light does not carry. It must persist. It must remain functional. It must survive impacts and decay. It must keep its purpose intact across time. The void does not prevent motion, but it removes almost every practical feature that makes motion useful to the civilization that begins it in that sense. Travel to Andromeda would be less like an extended mission and more like a transfer into a future too distant to share. The craft would move through space, but its meaning would drift through time. The departure galaxy would recede into history before the destination became an environment. The longest part of the journey would not be arrival or discovery, but endurance without context. That is the deeper severity of motion across the intergalactic gap. A path exists in the geometric sense. Gravity, velocity, and direction can define it. Yet for anything emerging from human timescales, the path does not behave like a road to a place. It behaves like a separation so large that movement itself becomes almost invisible. And arrival, even if physically possible, becomes disconnected from the life that once made the journey meaningful. Andromeda is often introduced as the nearest large galaxy to the Milky Way, and that description is scientifically correct. It is part of the same local group, gravitationally connected to our galaxy, close enough to be studied in great detail, and bright enough to be seen without a telescope from dark skies. Yet the word nearest can easily mislead. It sounds comparative in a way that feels comforting, as if the closest example of something might also be the most reachable example. In astronomy, that is not always true. A nearest object can still be far beyond any practical form of access. Andromeda shows this clearly, because it is not an extreme case chosen to make the universe look larger. It is the favourable case. It is the nearby major galaxy, the one placed at the beginning of intergalactic distance rather than the far end. If this object already sits beyond any journey that preserves human continuity, Then the rest of the extragalactic universe belongs to an even more severe category. The problem is not that current spacecraft are too slow in a temporary way. Current spacecraft are slow, but the deeper limit comes from the relation between distance, light speed, energy, and time. The fastest human-made machines have reached impressive speeds only within the gravitational environment of the solar system, often by falling close to the Sun or using carefully planned planetary encounters. Those speeds are extraordinary for engineering, but they are tiny beside the speed of light. Even a spacecraft moving at hundreds of thousands of miles per hour would take billions of years to cross the gap to Andromeda. That duration is comparable to the age of Earth itself. A mission beginning near the formation of the planet would still not fit comfortably inside the history of life and civilization as a connected project. This comparison matters because it separates improvement from transformation. Faster rockets, better engines, and more efficient trajectories could shorten some journeys within the solar system, and perhaps eventually make nearby stars less unreachable in principle. They do not turn intergalactic space into a normal extension of exploration. To do that, a craft would need to move at a significant fraction of light speed for millions of years of distance, and that brings new constraints rather than simple freedom. At a tenth of light speed, which is far beyond any macroscopic spacecraft ever launched, Andromeda would still require roughly 25 million years of travel from the Milky Way. That is not an engineering delay of the kind solved by a better schedule. It is a span long enough for large biological and geological changes to occur on the planet that sent the craft. At half the speed of light, the crossing still takes millions of years by the clocks of the galaxies, even before considering acceleration, deceleration, shielding, course correction, and energy supply. Relativity changes the experience of time for travelers moving very close to light speed, but it does not make the journey simple. To reduce the experience time dramatically, speeds must approach light speed very closely, and the energy required rises sharply. A massive craft cannot be pushed to such speeds without demands far beyond known capability. It must also slow down at the destination, which requires additional energy or an interaction with the target galaxy that would itself be difficult to control. High speed solves one part of the problem only by intensifying others. Dust grains, atoms, and radiation become more dangerous. Navigation becomes less forgiving. The stored energy of the moving craft becomes enormous. A collision with even a small particle can release destructive energy when relative velocity is high enough. The void between galaxies is thin, but it is not free of matter. And a journey measured in millions of light years gives rare hazards many chances to matter. Speculative ideas sometimes try to bypass this by proposing warp drives, wormholes, or other changes to space-time geometry. These concepts appear in serious theoretical discussions in limited forms, but they remain far from demonstrated technology and often require conditions or forms of energy not known to be physically available. They are useful as questions about the boundaries of theory, not as evidence that Andromeda can be reached. A scientific assessment has to begin with what is known to work. Matter moves below light speed. Information moves no faster than light. Energy requirements increase as speed approaches that limit. Space across millions of light years does not provide natural stations, fuel sources, or easy correction points. Within those rules, Andromeda remains inaccessible to ordinary exploration even though it is nearby among galaxies. The psychological difficulty is that space exploration has often advanced by turning unreachable objects into reachable ones. The Moon moved from myth and measurement to footprints and instruments. Mars moved from a point of light to a world mapped by orbiters and crossed by rovers. The outer planets, once only telescopic disks, became places visited by spacecraft, with rings, moons, storms, magnetospheres, and surfaces studied in detail. This history encourages the belief that distance is mainly a temporary barrier. It has often been true within the solar system. It may be partly true for the nearest stars if future civilizations develop propulsion far beyond current methods. But Andromeda is not another step in the same progression. The scale changes the nature of the effort. Solar system travel occurs within a shared human time frame. Interstellar travel to nearby stars already strains that frame. Intergalactic travel to a major galaxy breaks it. The destination is not simply far. It is separated by enough time that the origin cannot be expected to remain socially, biologically, or institutionally continuous with arrival. That is why the word destination must be used carefully. A destination is usually a place where arrival can complete the intention of departure. The travellers, or at least the society that sent them, can recognize the outcome. Andromeda denies that ordinary structure. A probe might arrive after an immense duration, but the report would take millions of years to return. A crewed vessel would become isolated from its starting civilization beyond any normal meaning of mission support. A civilization might send self-replicating machines or long-lived archives. But then the project becomes less a journey and more a transfer of influence into a future no one can oversee. Even success would not resemble exploration, as it is normally practiced. There would be no continuing conversation between the origin and the destination. There would be no sequence of missions steadily building a presence with feedback across generations. The time delay and travel time separate cause and result too deeply. This does not reduce the scientific importance of Andromeda. In one sense, it increases it. Since physical access is effectively denied, observation becomes the main form of contact. Telescopes gather light, spectra, motion, brightness changes, and resolve stellar populations. These tools allow Andromeda to become known without being visited. Astronomy is built around that kind of access. It accepts that most of the universe can be studied only through signals that arrive naturally, not by machines sent there. Andromeda is therefore both an accessible laboratory and an unreachable place. Its stars can be counted in great surveys. Its history can be inferred from stellar streams and chemical patterns. Its motion toward the Milky Way can be measured. Its future interaction with our galaxy can be modelled. None of these achievements require a spacecraft to cross the gap. They also do not make the gap less real. Knowledge travels more easily than matter because light is already on the way. The human role is to receive it carefully. The closest impossibility, then, is not a contradiction. It is a category that Andromeda forces into view. The galaxy is close enough to prove that other galaxies exist, close enough to reveal individual stars with powerful instruments, close enough to be part of our gravitational future, and close enough that its light is a familiar feature of dark northern skies. At the same time, it is far enough that travel there exceeds the continuity of any known civilization, and perhaps any stable biological lineage. It is near in a cosmic catalogue and remote in every practical sense of motion. That distinction is one of the most important lessons contained in the distance. The universe does not arrange itself around human categories of reachable and unreachable. It allows an object to be visible, measurable, gravitationally related, and still beyond visitation. Andromeda is the nearest major galaxy, but nearest does not mean close enough. It means only that every other large galaxy begins beyond a separation that has already defeated the ordinary idea of going there. The future of Andromeda changes the meaning of its distance without making that distance smaller. The Milky Way and Andromeda are not drifting apart like many galaxies across the expanding universe. They are bound together by gravity inside the local group, and measurements show that Andromeda is moving generally toward the Milky Way at about 110 kilometers per second along the line of sight. That speed is enormous by human standards, but it is small beside the separation it must work against. A galaxy can move hundreds of thousands of kilometers in an hour and still need billions of years to cross the space between two large systems. This is the first quiet correction offered by the future collision. The distance to Andromeda is not only too large for spacecraft, it is so large that gravity, acting continuously on two massive galaxies, still requires a span comparable to planetary deep time to bring them together. The approach is real. Yet it is almost motionless on any human scale. Andromeda rises and sets in the night sky with the turning of Earth. Its position can be measured with increasing precision. Its light can be studied in detail. But across a lifetime, the galaxy does not visibly swell toward us. The change is present in the mathematics of motion, not in ordinary sight. This slow convergence has been confirmed by measuring both the motion toward us and the more difficult sideways motion across the sky. For a collision or close encounter to occur, Andromeda must not simply be approaching. Its transverse motion, the motion across our line of sight, must be small enough that the two galaxies cannot simply pass far apart. Observations with space telescopes have helped constrain that motion, and models indicate that the Milky Way and Andromeda are likely to undergo a major encounter several billion years from now. The exact path remains uncertain because galaxies are extended systems, not solid bodies, and their dark matter halos begin interacting long before their bright disks overlap. Smaller members of the local group, including the Triangulum Galaxy and many dwarf systems, also contribute to the gravitational complexity. Still, the broad expectation is clear. The two dominant spirals of the local group are falling toward a shared future. The word collision has to be understood carefully. It does not mean that stars will crash into one another in large numbers. Stars are huge compared with planets, but the spaces between them are far larger still. When galaxies merge, their stellar populations mostly pass through one another, with individual stars rarely meeting directly. The main interaction is gravitational. The galaxies distort each other. Their disks stretch. Tidal forces pull out long streams of stars and gas. Orbits that were once part of organized spiral rotation are rearranged into new paths. Gas clouds can collide and compress, because gas is diffuse and fills more volume than stars do. That compression may trigger new waves of star formation. Dust lanes may be disturbed. The central regions may become active in new ways as gas loses angular momentum and moves inward. The merger is therefore not a simple impact. It is a long gravitational reshaping, a process that begins before the galaxies overlap and continues long after their first close passage. The Sun, if it still exists as a star in its later life, is unlikely to collide with another star during this event. It may be thrown into a different orbit around the combined system, perhaps farther from the centre than it is today, or into a path unlike its current motion in the Milky Way. The solar system, if still intact, would experience the merger mainly through the changed gravitational architecture of the galaxy around it. By that time, however, Earth itself will have been transformed by the Sun's evolution. Long before the Milky Way and Andromeda fully settle into one system, the increasing brightness of the Sun will have altered the conditions that now allow liquid water to persist on Earth's surface. The future galactic merger is therefore not a human catastrophe waiting on the calendar. It belongs to a time when the familiar Earth will already be gone as a stable home for present life. This helps keep the event in its proper scale. The merger is important not because it threatens the present world, but because it reveals how galaxies change when gravity is given enough time. The same distance that defeats deliberate travel will be crossed by the slow, mutual fall of two massive systems. No engine is needed. No route is planned. No one has to preserve purpose through the journey. Gravity simply acts. always weak across vast separations but never absent, and over billions of years its persistence becomes decisive. This is why the future of Andromeda is not a contradiction of its unreachable distance. It is the other side of the same fact. For a traveller, the gap is a barrier because life and civilization are short. For galaxies, the gap is part of their natural dynamics because their histories unfold over billions of years. The universe has time to do what no mission could meaningfully do. During the first close passage, the two galaxies would not immediately become one smooth object. They would pull at each other, pass through, separate again, and then return under gravity. Each encounter would convert ordered motion into a more mixed structure. Spiral arms would be disrupted, stellar streams would extend into the surrounding halo, gas would be heated, compressed, consumed by star formation or driven inward. The central black holes, each embedded in its own galactic nucleus, would eventually sink toward the middle of the new system through interactions with surrounding stars and gas. Over still longer periods, they may form a binary pair and ultimately merge, releasing gravitational waves. By then, the visible form of the combined galaxy would have changed greatly. The flat spiral disks of the Milky Way and Andromeda would likely give way to a larger elliptical or lenticular system, depending on the details of gas content, orbital motion, and the influence of other group members. A future observer inside it would not see two separate grand spirals dominating the local group. There would be one larger stellar system, built from both. The process can sound dramatic, but its pace remains almost beyond comprehension. A close passage might unfold over hundreds of millions of years. The full settling of the remnant could take billions more. No single living observer could watch the event as a sequence in the ordinary sense. Even long-lived civilizations, if any existed then, would experience it through measurements passed across deep institutional time. The night sky would change, but slowly, with Andromeda broadening over ages, its structure becoming clearer, its tidal effects more apparent, until the distinction between the two galaxies began to fail. What now appears as a faint distant object would eventually become a major presence across the sky. Later still, after repeated interactions, the separate identities of the two systems would become historical rather than spatial. Stars born in the Milky Way and stars born in Andromeda would share one gravitational home. This future gives Andromeda's distance a second meaning. It is not permanent within the local group. Gravity is already answering it, but the answer is written in a timescale too large to serve exploration. The gap will close not because it has become manageable, but because both galaxies are part of a bound system whose long-term evolution is governed by mass and motion. The universe does not need to make the distance usable in order to erase it. It only needs to let gravity continue. That distinction is important. Human thinking often treats distance as something to be overcome by speed. Galactic evolution overcomes it by patience and attraction. The result is not arrival in the intentional sense. It is assembly. The Milky Way and Andromeda will not meet because one has travelled to the other as a destination. They will meet because neither is isolated, and because their shared gravity has been shaping the future from the beginning. In this way, the approaching merger is both humbling and clarifying. It shows that Andromeda is not a fixed point forever beyond influence. It is already involved with the Milky Way, already part of the same gravitational story. At the same time, it shows why involvement is not the same as access. The future collision will take longer than the time remaining for Earth to resemble its present self, longer than the entire span of complex human history by an almost meaningless margin, and longer than any ordinary continuity of culture can be expected to survive. The distance to Andromeda can be closed by galaxies, but not by anything that depends on human time. Gravity has an answer, but it speaks slowly, And its answer is not a journey. It is a merger so gradual that the two great spirals will lose their separate forms before any observer could experience the crossing as an event. The distance to Andromeda belongs to a larger condition that is easy to miss because the local group still feels active and connected. The Milky Way and Andromeda are approaching each other, and their future merger shows that gravity can still hold nearby galaxies together against the expansion of the universe. This local binding is real, but it is not the general rule everywhere. On larger scales, the space between galaxy groups and clusters is expanding, and that expansion is not slowing down in the way early cosmology once expected. Observations of distant supernovae, the cosmic microwave background, and the large-scale distribution of galaxies show that the expansion is accelerating. The name given to the unknown cause of this acceleration is dark energy. The term does not identify a familiar substance. It names a measured effect. The expansion of space is speeding up over cosmic time. This matters for Andromeda because it separates the reachable universe from the observable universe. A galaxy may be visible in the sky, and still be permanently beyond physical contact. Light from faraway galaxies can reach Earth because it began its journey long ago, when those galaxies were closer and the expansion had less distance to stretch. But a signal sent now toward many of those same galaxies would never arrive. The space between origin and target would expand too quickly for the light to close the gap. The object can remain part of the visible past while being absent from any reachable future. This is one of the most severe facts in cosmology. The universe is not simply a large arena waiting to be crossed. It has horizons, boundaries created by the behavior of space-time itself. A horizon is not a wall made of matter. It is a limit on possible communication. Beyond it, events can occur. Stars can form and die. Galaxies can continue evolving. But no information sent from there now can ever reach here, and no information sent from here now can ever reach there. The horizon is defined by expansion and time, not by any material barrier. In the present universe, the local group lies safely inside a region where gravity dominates over cosmic expansion. The Milky Way, Andromeda, the Triangulum Galaxy, and the many smaller dwarf systems around them form a bound structure. Their mutual gravity is strong enough to prevent them from being carried apart by dark energy. This is why Andromeda is approaching rather than receding. Yet beyond the local group, the situation changes. Nearby galaxy groups may still be observed in great detail, and their light may continue arriving for a long time. But they are not necessarily available as future destinations even in principle. The farther a galaxy is, the more the expansion of space between it and the local group matters. At very large distances, recession becomes dominant. This recession does not mean that galaxies are flying through space faster than light in the ordinary local sense. It means that the space between widely separated regions is increasing, and general relativity allows the distance between those regions to grow faster than light could cross it. No object locally outruns a light beam beside it. The total separation grows because the underlying geometry expands. That distinction is important because it keeps the statement within known physics while preserving its full consequence. For the most distant galaxies, the issue is not only practical difficulty, it is causal disconnection. Even unlimited patience cannot make a message arrive if the expansion forever adds distance faster than the message can remove it. This gives the present cosmic era special importance. The sky now contains evidence of a universe far larger than the local group. Telescopes can observe galaxies in every direction, at many distances and many ages. Deep surveys reveal faint systems whose light began travelling when the universe was young. The cosmic microwave background records a still earlier stage, when the universe became transparent enough for light to move freely across space. From these signals, astronomers reconstruct a history that includes the formation of the first atoms, the growth of structure, the birth of galaxies, the enrichment of matter by stars, and the emergence of clusters and filaments. The visible universe is not only large, it is informative. It carries a record of its own development. But this visibility is not guaranteed forever. As expansion continues to accelerate, galaxies beyond the gravitationally bound neighborhood will recede faster and farther. Their light will be stretched to longer wavelengths, dimmed and delayed. Over immense periods, many will become impossible to detect. A future observer inside the merged descendant of the Milky Way and Andromeda may see a sky dominated by stars within one large local galaxy, while the evidence for the wider population of galaxies fades beyond reach. The universe will still contain those distant systems in a global sense, but they will no longer be observable from that location. The knowledge available to future astronomy would be narrower, not because future observers are less intelligent, but because the signals would no longer arrive. This is a different kind of loss from ordinary ignorance. It is not a gap that can be closed by building a better instrument after the fact. If light from beyond the horizon cannot arrive, no telescope can collect it. If the wavelengths have been stretched too far and the sources have dimmed beyond detection, the information has effectively left the local observational universe. Cosmology, in that future, could become harder to infer. The expansion of the universe, the existence of other galaxy groups, and the broader history of structure might not be obvious from the remaining sky. A civilization arising in that era could live inside a large galaxy and see mostly its own stars, globular clusters, remnants, and local gas, without the external reference of countless receding galaxies. The evidence that once revealed the expanding universe would be reduced or absent. The cosmic microwave background would also be stretched and cooled to extraordinary faintness. The early universe would not be gone from reality, but its observable traces would be harder to recover. This possibility gives the current view of Andromeda a broader meaning. Andromeda is not only a nearby galaxy whose distance is difficult to cross, it is part of the last major structure that will remain gravitationally available to the Milky Way over the longest future. The local group will not expand away from itself. It will consolidate. The large galaxies will merge. Smaller galaxies will be absorbed or rearranged, and the resulting system will become increasingly isolated as everything beyond the bound region disappears behind cosmic horizons. In the near present, Andromeda represents separation across intergalactic space. In the far future, it represents the boundary of what remains connected. The same object that now appears unreachable by travel will eventually become part of the local remnant, while galaxies much farther away become unreachable even to light sent from the future. This contrast is important because it prevents a simple conclusion. The universe is not only too large for present travel, it is changing in a way that reduces future contact across its larger scales. Expansion does not pull apart galaxies that are already bound tightly enough, and it does not overcome the forces holding stars, planets, or clusters together. It acts mainly across the largest separations, where gravity is too weak to reverse the widening of space. There, the long-term trend is isolation. Groups and clusters remain as local islands of structure, while the distances between them increase. The observable universe becomes less connected as time passes. The distance to Andromeda is therefore not the outer edge of the problem. It is the nearest example of a scale that still belongs to the gravitational neighborhood. Beyond it lies a universe that is not merely farther, but progressively less available. Other galaxies can be observed today because their ancient light is still arriving. Many cannot be reached now, and in time many will not even be seen. This gives the present moment a scientific value that is easy to overlook. The cosmos is visible now in a way that may not be possible forever. The sky still contains the evidence needed to know that the Milky Way is not alone, that galaxies fill space in vast numbers, that the universe has expanded from a hotter and denser past, and that dark energy is shaping its future. Andromeda helped open that understanding by proving that another large galaxy existed beyond our own. Its distance now helps clarify the deeper condition. The universe allows observation across scales that travel cannot follow, and even observation is temporary on the longest timeline. The closing cosmos is not a sudden event. It is a gradual narrowing of causal contact. Light continues to arrive, galaxies continue to evolve, and gravity continues to bind the local group. But beyond that bound region, the larger universe is already moving towards separation, one horizon at a time. Andromeda remains one of the clearest examples of how astronomy can make an object familiar without making it close. It is visible to the unaided eye under dark skies. It has been recorded for more than 1,000 years. It has a stable place in catalogues, photographs, sky maps, and public memory. Its direction can be learned, its shape can be imaged, its stars can be measured, and its future with the Milky Way can be modelled. In many scientific contexts, it is nearby. It is part of the local group, bound to the same gravitational environment as the Milky Way. It is the nearest major spiral galaxy, a system close enough for large telescopes to resolve stellar populations, trace streams in its halo, study its satellite galaxies, and compare its history with that of the Milky Way. Yet the same object stands beyond a distance so large that ordinary meanings of closeness fail. This is the central lesson that survives all the measurements. Nearness in astronomy is not a single idea. There is observational nearness, where light is strong enough and detail rich enough for study. There is gravitational nearness, where two systems influence one another over time. There is physical nearness, where travel, communication, and shared time remain possible within a coherent frame. Andromeda satisfies the first two conditions, but not the third. It can be seen and measured. It is falling toward the Milky Way through the slow dynamics of the local group, but it cannot be reached in a way that preserves the ordinary continuity of a mission, a civilization, or a conversation. That difference is not a failure of human effort. It is a property of scale. The distance of about 2.5 million light-years places Andromeda close among large galaxies and nearly unreachable for matter moving from Earth. Light crosses the gap because light has no need to endure, decide, repair itself, or carry a society. It simply moves at the speed allowed by nature. A spacecraft would carry mass, structure, vulnerability, stored energy, and purpose. A signal would carry information, but not a shared present. This is why the faint glow in the sky is so scientifically important and so severe at the same time. It grants access to the past state of another galaxy, while also proving the size of the gulf between access and arrival. The history of Andromeda has repeatedly corrected human assumptions. It was first treated as a small cloud, because that was what the eye and early instruments could honestly report. It became a nebula in a catalogue because its true nature could not yet be separated from other cloudy objects. It became a decisive galaxy when Cepheid variables gave astronomers a way to measure its distance. It became a detailed system as modern telescopes resolved stars, mapped structure, and revealed evidence of mergers and satellite companions. Each stage made Andromeda more real, but none made it smaller. The increase in knowledge widened rather than softened the conclusion. The object was not a local haze. It was a vast galaxy. The Milky Way was not the whole universe. It was one member of a larger population. The galaxy that looked like a quiet blur contained roughly 1 trillion stars and a central black hole far more massive than the one at the centre of the Milky Way. The soft light came from a structured system with a disk, bulge, halo, dust, gas, streams, and smaller companions. The more precisely the object was understood, the more sharply the distance had to be accepted. That is the unusual discipline of astronomy. It does not reduce wonder by replacing appearance with measurement. It often makes the appearance more difficult, because the measured object is larger and farther than the first impression allowed. Andromeda also clarifies the limits of comparison. The Moon is distant by human travel standards and close by astronomical ones. The planets are remote but reachable by machines. The nearest stars are so far that present technology turns them into journeys of deep historical duration. The Milky Way itself is so wide that light takes about 100,000 years to cross its bright disk. Andromeda lies many times farther than that width. It is not positioned just beyond the edge of the familiar galaxy. It is separated by a region where stars are sparse, matter is thin, and the main endpoints are 2 large galaxies moving slowly within their shared gravitational field. The word neighbour can remain useful only if its meaning is carefully held. Andromeda is a neighbouring galaxy, but a neighbouring galaxy is not like a neighbouring world, a neighbouring star, or even a neighbouring region within the Milky Way. The category is larger, and the distance is correspondingly larger. This is why the title of nearest major galaxy can be both correct and misleading. It identifies Andromeda's rank in the local cosmic environment, not its accessibility to anything launched from Earth. The same distinction applies to time. Every photon now arriving from Andromeda left that galaxy when Earth was in a different biological chapter. Early humans had not built cities, written records, or scientific instruments. The species that would later measure the distance had not yet become the world-shaping force it is now. The light crossed the void while climate shifted. Animals evolved and vanished, ice advanced and retreated, and human cultures eventually appeared and transformed the planet. By the time that light reached telescopes, it had become a record from an era beyond living memory and far beyond written history. This delay is not a flaw in observation. It is the condition that makes the observation possible. Andromeda is seen through ancient light because all distant objects are known through signals that take time to arrive. The nearby galaxy is therefore not nearby in time. It is offset from Earth by a past older than humanity's known story. A message sent there would face the same delay in reverse. A reply would return after a span longer than the development of the human lineage from its early ancestors to the present. Communication across that distance may be physically possible as transmission, but it does not form a conversation in the normal sense. The endpoints cannot rely on shared context over such duration. Meaning would have to survive not only space, but evolution, extinction, cultural loss, and planetary change. The future merger of the Milky Way and Andromeda adds another layer rather than a solution. The 2 galaxies are moving toward each other, and gravity will likely bring them into a major encounter billions of years from now. This does not make Andromeda reachable. It shows that galaxies operate on timescales where separations that defeat travellers can still be altered by patient dynamics. Gravity has no need for a mission plan, no need for continuity of intention, and no need for a living observer to experience the process. The galaxies will approach, distort, pass through, and eventually settle into a combined system if current models are broadly correct. The distance will be changed by cosmic evolution, not by travel in the human sense. This future reinforces the lesson rather than weakening it. Andromeda is connected to the Milky Way, but connection across galaxies is not the same as access across human time. Beyond the local group, the conclusion becomes even stricter. Many galaxies visible today are not merely farther than Andromeda. They are being carried away by the expansion of space, and some are already beyond any future contact by signal sent now. The observable universe is larger than the reachable universe in the far future. As expansion continues and distant galaxies fade beyond practical detection, the merged remnant of the Milky Way and Andromeda may become increasingly isolated. The wider cosmic population that modern astronomy can still observe may become hidden from any future observers inside that remnant. In that setting, Andromeda's current visibility has a particular value. It is part of the evidence available during a period when the universe can still reveal much of its structure. It helped show that the Milky Way is not alone, and it now helps show that visibility is not possession. The universe can be open to measurement while closed to travel. It can permit knowledge across distances that bodies cannot meaningfully cross. This is the calm, final meaning of Andromeda's distance. The galaxy is neither a simple destination nor a remote abstraction. It is a real, nearby member of the local cosmic environment, and it is also separated from the Milky Way by a gulf that changes the meaning of space. Time, communication, and exploration. Its light can enter the eye, but its present cannot. Its future is tied to the Milky Way, but its current separation cannot be bridged by any ordinary understanding of motion. It is close enough to have reshaped the history of cosmology, close enough to reveal stars and structure, close enough to share a gravitational fate, and still far enough to remind astronomy that seeing is not arriving. Andromeda is the galaxy next door only when galaxies are doing the measuring. For human time, human machines, and human continuity, it remains the nearest great wall of distance in the night sky. In the end, Andromeda remains calm in the sky because distance gives it that appearance. Its light arrives without sound, without motion visible to the eye, and without any sign of the long crossing behind it. Yet within that faint glow is one of the clearest lessons astronomy has ever offered. The universe can make something visible while keeping it almost entirely beyond reach. It can place a galaxy close enough to be seen from Earth, and far enough that its light began travelling before the human story had taken its present form. It can bind two great spirals together by gravity, and still require billions of years for that connection to become a merger. Andromeda is not frightening because it is hostile. It is severe because it is honest. It shows the scale of the cosmos without adjusting that scale to human expectation. The same distance that once hid its true nature now makes it scientifically valuable. Because every measurement carries both knowledge and limitation. The galaxy can be mapped, studied, compared, and understood more deeply with each generation of instruments, but it cannot be brought into the present, and it cannot be turned into an ordinary destination. That difference remains. Seeing is not arriving, knowing is not crossing. The nearest major galaxy is close only in the language of galaxies, and that language belongs to structures whose lives unfold over spans far longer than civilizations. Species, or worlds, remain unchanged. The quiet light from Andromeda therefore leaves a final impression that is not despair, but proportion. The cosmos is not smaller because it can be studied. It is more clearly immense. It allows understanding to travel farther than bodies, and it leaves the rest to time, gravity, and patient light.